I'm pleased to be talking today about cooperative sensing for automated vehicles. David mentioned that I do work in security, and that has been one of the central features of my research over the last decade. But today I'm kind of stretching a bit, and I'm going to talk about something that's basically brand new in our minds. So it's going to be fairly high level and maybe get some feedback from you. And it won't have too much to do with security, although it will impinge on it at least in one respect. So here I go. I'm going to share my screen and we can begin talking. So I'm the director of the Radio Navigation Laboratory at the University of Texas at Austin. And we have a fine group of graduate students and a postdoc. Of these graduate students, and the postdoc, 3 have played a special role today. Daniel's work is featured almost exclusively today, and Lakshay and Peter have also helped a great deal in refining some of the ideas that will be presented. We are doing this work within a group called UT Saves for Situation Aware Vehicular Engineering Systems. It's a group that was created here at UT to engage with auto manufacturers and other industrial players who care to work in the automated vehicle space. And today's work really is at the nexus of communication and sensing and data analytics, which are the 3 areas that UT Saves are trying to address. Today's work in particular is funded by Honda through UT Saves, Honda Research America. So to start with a question, how reliable must self-driving cars be? Should they have 100 million miles between system-caused fatality? That is equal to the current human level. If you talk to Elon Musk, he'll say, no, it's good enough if they just have 2 times human reliability, say 200 million miles between a system-caused fatality. Ford in 2019 produced a document that said, no, it ought to be 100 times human reliability, or else we won't be able to encourage people to adopt the technology. And Intel and Mobileye went even further a little earlier on, where they said, nah, it should be 1,000 times human reliability. My own guess is that it's somewhere between 2 times and 100 times. And what I say is, what I mean by that is that there comes a moral imperative when you get close to, say, 100 times human reliability, that these automated vehicles should be deployed to save lives. Why not deploy them at 2x? Well, because there are feedback effects. Think about this. At only 2x human reliability and with a fleet of 1 million vehicles, which is about like what the Tesla current fleet has, one would expect a vehicle-caused fatality, so a fatality that could be traced to a line of code in the vehicle, traced to a decision made by an engineer, every 5 days. And it's my belief that no manufacturer could withstand the ensuing product liability lawsuits and the reputational damage of a fatal collision every 5 days, traceable to decisions made deliberately by the manufacturer. So I don't think 2x is going to be viable, not just for moral reasons, but for reasons of reliability and product liability lawsuits. So how do you achieve extremely high reliability, say nearing 100 times human performance? Well, each subsystem will have to be allocated a very tight risk allocation. So each subsystem will be allowed to make mistakes only very, very rarely. But this is the key. Automated vehicles themselves are going to be much more perceptive of risk than we are. And we have a kind of sixth sense when we drive. We know that there might be something lurking around a corner and we behave perhaps more cautiously because of that. But automated vehicles will have a better quantification of this risk and will have a better sense because they'll have persistent sensing and persistent monitoring of the environment. So they'll know better than we do exactly the risk of proceeding through an intersection, and for that reason are likely to drive much more cautiously than we do. So in order to keep their risk within the tight allocation that we suppose will be required, they'll either have to choose from among these options. They'll either have to drive uncomfortably cautiously, say below 25 miles an hour, just creeping through the streets. Or they'll have to cooperate. They'll need to share data to eliminate blind spots, maybe between each other, or maybe between themselves and infrastructure in the area. So we call this the automated vehicle trilemma. We say you need to either cooperate, or you'll crawl, or you'll crash. And it's a trilemma because each one of these brings its own negative consequences, even the cooperation, which is something I'll speak to later on. To play around with the notions of this trilemma, we've been developing a sensor platform that we call the Sensorium. It's got a lot of the same sensors that you would expect in an automated vehicle, but we don't try to close the loop around the Sensorium. Our focus has been on just the sensing part. What can we know about the environment? How much can we assess risk-wise about the environment? And we've got on this Sensorium, we've got specialized GNSS receivers that we build on the inside. We've got several radar sensors, dual camera sensors, 3 different kinds of inertial sensor. We're trying to better understand the limits of sensing with this box. And just to make sure that we could cooperate, we built a sibling box so that we can share data and assess the benefits of collaborative or cooperative sensing. Let me give you a sense for what this would look like and why it needs to be addressed in a scenario that might seem familiar to you. This is an image that we took in downtown Austin a while back, where the ego vehicle is taking the picture. And so from the perspective of the ego vehicle, although you can't see it because it's a black and white photo, the light is green, and the ego vehicle has every right, legally, to proceed through the intersection at about 35 miles an hour. However, the bus just to the left of the ego vehicle is in a turning lane, turning left down the road, and is blocking sight to the left. There's a large blockage to the left where the ego vehicle might be uncertain about what potential occupants might be there and their intent and their future trajectories. So even though the ego vehicle is legally entitled to move through this intersection, it might not wish to do so at its full speed because it senses heightened risk due to blind spots. And in fact, in this case, there was a pedestrian lurking behind the bus who decided he was going to make a run for it even after the light was green. It would have been a nasty collision had the ego vehicle taken its full legal entitled velocity through here. However, from the perspective of the other side of the street, there is a vehicle, a cooperating vehicle, that is taking video footage of the same incident. And the cooperating vehicle can see what's behind the bus and recognizes that the pedestrian is on a potential collision course with the ego vehicle. So just getting access to these sensing data from across the street would be enormously valuable for the ego vehicle, if nothing more, so that the ego vehicle, when it got such sensing data and was told that there wasn't any additional risk, it could proceed through the intersection at a faster rate. So the ego vehicle, given any kind of uncertainty, is going to respond by going very slowly, and this additional sensing in effect buys back miles per hour. You can proceed with greater confidence through the intersection. Now, quantifying the benefits of sensor sharing requires an assessment of the effect of such sensor sharing on the cost density function. And this cost density function is kind of a cost of collision. And you can think of it as some way of saying, well, if there is a collision, what would be the cost in terms of the relative velocities? What would be the cost in terms of the traffic participants? You know, you have pedestrians versus cars versus cyclists. And there will be a distributed range of cost outcomes that we try to capture in a distribution function. Let me see if I can illustrate this with a few drawings here. What I've tried to do is to draw in this diagram a bird's eye view of the same intersection we were in just previously. You see, can you all see my cursor? Are you able to see that?
Yep.
Okay. You see the bus just left to the left of the ego vehicle, which is blocking the pedestrian lurking on the street corner. There might be a bicyclist up the street that is not in view of the ego vehicle, and a car over here. This is, in this case, the collaborative vehicle, but for the purposes of this discussion, we're not even going to think about that vehicle collaborating. And over on the right-hand side, I've drawn the axes preparing to draw a cost PDF, probability distribution function. This distribution is trying to say, what do we expect the cost to be for collisions sometime in the future, maybe 5 seconds out? Now, let's take a look at this same situation from the perspective of 3 different observers. The first observer I call the omniscient observer. And this observer knows the ontology of the situation. So he knows the existence of all the different traffic participants. He also knows the initial conditions of all the traffic participants and the evolution over the 5-second propagation interval of each traffic participant. And there's just no uncertainty here in terms of location or velocity, or, as I say, ontology. This is an omniscient observer. This is only available in the mind of God or in the mind of whoever's running the grand simulation we're in, if you go for that. But this observer has full knowledge. And because of the full knowledge, cost is certain. So in this particular case, the ego vehicle is projected to collide with a cyclist who may be running the green light, the red light for the cyclist. And that will happen 5 seconds into the future. So the cost at 5 seconds to the future might be viewed as a direct delta function, very high cost and well-known value of that cost. Okay, but this is not the case for any scenario we could imagine. An omniscient observer is not easy to query. So let's imagine we go to a different type of observer. This one again, we see from the bird's eye perspective. This one is an omnivident observer. So it sees everything, but it can't know everything. It doesn't predict everything. It can't get into the mind of the traffic participants. So it has a certain ontology. It knows all about what traffic participants are present. It knows exactly their initial conditions, but it doesn't know exactly what will happen over the next 5 seconds. And so it's trying to offer a cost that will apply 5 seconds from now, and it must do so with a probability distribution. So what it's saying is, look, this is a pedestrian, and it's highly likely the pedestrian will stay here at the corner and will be there in 5 seconds. But there is a low probability that the pedestrian will try to run across the to walk across the crosswalk, even though the light is green for the ego vehicle. And there is some crazy probability that the pedestrian will step off into the middle of the intersection too. So I wasn't able to really illustrate with these points how unlikely that is, but you can take these points here to be rather unlikely. Similarly for the bus, it's most likely to stay where it is, but it's going to be making a left-hand turn, and so its density in the 5-second horizon might be along this line. And the car has something similar. The bicyclist is known to the omnivident observer, and the observer has a probability associated with the bicyclist being in the intersection. So all of this combined, together with the relative velocities and the kinds of costs that would be associated with each collision, would leave you with a cost distribution at a 5-second horizon, whose mean you can consider to be the risk for the ego vehicle. The risk we define to be the mean of the cost. So at this point, the omnivident observer is giving us a bound on what one could do with cooperative sensing. The omnivident observer is like the ideal pooled data in a cooperative sensing situation. The sensing doesn't tell you what the participants will do in the future, but the sensing can help you to categorize the participants and to count them. Now, the perspective of the ego vehicle is rather different. Let's assume that there isn't any cooperation going on. The ego vehicle doesn't see the pedestrian over here, doesn't see the cyclist, but does see the bus and the car on the other side of the road. And so it can make some projections about what the car will be doing in 5 seconds from now. and can make projections about what the bus will be doing. But it has uncertain ontology. It doesn't know the existence of participants that may be lurking in blind spots. It also has uncertain initial conditions, even for those participants that it recognizes. It doesn't quite know where they start and with what velocity they start. And then it has uncertain evolution. It doesn't even know what will be the evolution precisely of each one of the participants that it observes, let alone the participants that are lurking in blind spots, the ones that it can't observe. So the ego vehicle, apart from trying to model the evolution of those participants it sees, is going to try to have to conjecture the existence of some possible participants emerging into the scene. You can kind of think of this as a diffuse miasma that sort of seeps out from all blind spots areas into areas where that could be collisionable. So for example, it says, you know, I can't see behind the bus here. And so I'm going to assume that there might be something there. And if there is something there, well, then these points could be where that something would be 5 seconds from now. Unfortunately, not knowing what's behind the bus, since it's a blind spot, you don't even know what type of participant might be there. A cyclist, a pedestrian, maybe it's a different type of pedestrian, you know, a younger or older pedestrian. These different types have different probability models associated with their evolution. This would be something of a model associated with likely participants in this lane, which is a bike lane, so you would tend to draw it out a little bit longer. This is all very notional at this point, and you can kind of appreciate the difficulty of really getting a nice, honest probability distribution for the cost. It's actually easier in the case of the omnipotent observer because you can project things according to the type, but for the ego vehicle, it's really at a disadvantage in multiple ways. Uncertainty in all of these three areas. And yet this is the situation that an ego vehicle faces if it's not cooperating. Now, a couple of things to keep in mind. Both the omnipotent and ego vehicle, they would like to evolve path distribution in a type-specific way. For example, they'd like to say, well, grandmothers walk more slowly and more cautiously than teenagers. And so they'd like to be able to recognize types and have things evolve in that way. Ultimately, though, something I didn't mention in all of this is that a propagation engine must also take into account interaction between traffic participants. For example, some participant will see B, and it might slow down. And B will notice that A is slowing down, and it might speed up. And this kind of back and forth opens up just a host of possibilities for how one would approach this problem. And David Friedrich-Kyle, who's on the call today, and I have had a couple of interesting discussions about this. David, under Claire Tomlin, has done some interesting work, and I just think it's neat to recognize this point, and it's been a kind of theme of Claire's work over the years, that interaction cannot be ignored, cannot be avoided, because it's inherent to the dance between participants. However, it is not easy to analyze, and you might not be able to look a full 5 seconds out into the future because of all of the potential outcomes. Now, our first efforts at propagation and cost distribution quantification, they've been based on a very simple model. We started with an occupancy map, and then we went to a dynamic occupancy map, and we have a basic rudimentary universal diffusion model. So we don't even try to distinguish by type at this stage of our research. We're just trying to pretend that everybody is a particle, and that there are particles in places where we have blind spots. So we have taken a random finite set approach to the dynamic occupancy map, and this is work done by my student Daniel in a recent paper published at ICASP here in 2020. The idea being that we have divided up the world into cells, and there is a probability associated with each cell. The cell is empty with probability 1 minus r, and it's occupied with probability r, and if occupied, well, it has a distribution of p of x, a spatial distribution. And that can come with also a velocity distribution. And then this distribution can be thought of as associated with particles that evolve over time. So particles can migrate from one cell to the next over time, and might follow a diffusion model that is conscious of the environment. Say you tend to expect that pedestrians will move back and forth on sidewalks and not jump into the street. But it might have to allow for some irregular behavior of particles, even so that you can accommodate some of the crazy things that do occur on roads. After some time, you can allow this thing to run forward, and then you can ask yourself, how does it interact? So as you shine your cameras into an area, you're able to identify some of these particles, recognize their velocities, and ensure that, that you can track them. Or you might have seen the cells that had previously been marked with particles, and now you recognize that they are free of particles, and so this prior probability drops. This R probability drops. Anyway, this has been the way that we've been working on this so far, and we recognize that it's a terribly rudimentary approach, but it has the benefit of not having to ask hard questions about the type of vehicles and their evolutionary paths, and yet it still offers us a way of addressing the part of the work that we're interested in, namely laying out these cost density functions and understanding how they are affected by cooperative sensing. Now, back to our trilemma. Remember that it was cooperate, crawl, or crash. And a trilemma is a choice between three undesirable options. So you might be asking, why is cooperation undesirable? It sounds like cooperation is a good thing. We were taught in kindergarten that we should cooperate. It doesn't sound undesirable, even from the point of view of an automated vehicle. However, there are burdens that come upon that come with cooperation that many automated vehicle manufacturing companies would wish to avoid. I actually sat in one of the Google or Waymo cars a while back, and I asked the navigation lead for the project whether he was considering cooperating with other vehicles, even within the Waymo fleet. And he pointed out that the Waymo fleet does cooperate by pooling their data at night, but they don't do any real-time cooperation. And he said cooperation between a Waymo vehicle and, say, a cruise vehicle was out of the question. Anyway, I pressed him further, and I said, well, why not cooperate? He said, no, we've got to take an ego vehicle mentality. That's the way, that's the safest way to approach this. And I disagree. I believe that cooperation is much safer than assuming that you can make all do all decision making at the ego vehicle. But I have a full awareness of the downsides of cooperation. Let's take a look at each of these. First, cooperation requires that each vehicle have a precise pose estimate within a common frame. You have to be able to agree on the map that you're in order to cooperate. And for example, the Waymo vehicles have a map that is shared among all Waymo vehicles. But if you ask whether a certain feature in that map would have the coordinates that the map indicates, if a surveyor came in and checked those same coordinates, that same feature, Waymo will tell you, no, it'll only be loosely aligned, say in a WGS84 reference frame. And we don't care, because all we care is that we are correct with respect to our map. But if now the Waymo vehicle needs to talk to a Ford vehicle, well, they better be working from the same map. And the common reference frame that you would tend to agree on after negotiation would be something like an international terrestrial reference frame that is used in geodesy. And it's harder to lock yourself to a geo-referenced reference frame than to just a local one, because now you have to care about where the overall position is of the features. But we don't believe that this one is too hard a problem. We've been doing research in urban precise positioning. And this last year we published this paper, actually just a couple of weeks ago, it came out in the IEEE Intelligent Transportation Systems magazine, where we took our Sensorium into the deepest urban area we have here in Austin, and were able to get 14-centimeter positioning in the horizontal anytime our system registered a so-called integer ambiguity fix with the carrier phase differential system. And we were able to get better availability of that fix than any current system that's ever been published on. So, and the availability was up around 86%. So it's not perfect yet, but it's fun work, and it's exploring the limits of what you can do with extremely good positioning, even in dense urban areas where GPS signal blockage and multipath are both very common. So we believe that this problem is surmountable. What about the other problems? What about the difficulty of ensuring trustworthy data? You know, maybe the cooperation you're getting is between you and an Uber vehicle. And we all know the history of Uber and, you know, the dubious morality of Travis Kalanick. So maybe Uber is going to corrupt the data before sending it across to you, and thereby cause a competitor to make a mistake, right? So it might be cooperative in principle, but it might be malicious in the execution, just because these companies that need to be cooperating are in fact rivals of each other. So how would the ego vehicle ensure that the data it's receiving are in fact trustworthy? How could it ensure that the data can be ingested into its estimation algorithms and could be folded into the algorithms that adjust the probability distribution for the cost? Well, this is not an easy problem to tackle. There are many sensors that are feeding into one's own vehicle, the ego vehicle, and the other vehicles who are participating. You can have GNSS, radar, vision, lidar, other sensors. Each one of these sensors has its own failure modes, even in a non-malicious way. They fail just for, you know, GNSS fails under jamming. Radar can fail when there's a high congestion of other radar transmitters in the vicinity. And vision can fail when it misinterprets something. Now, add to that the possibility that somebody might be carrying out an attack on these sensors, and then add to that the possibility that a cooperating vehicle might deliberately cause corruption of the data or deliberately adapt the data to their needs before sending it off. And you've got 3 different levels of integrity problems using data from other vehicles. Extra platform sensing is when we pull in data from other vehicles. In the shipping world, it's AIS. In aviation, it's ADS-B. In ground vehicles, we talk about V2X. Getting these data would imply getting the local sensing from one of these protocols and knowing whether the data arrived without any malicious corruption or whether they arrived without any problems of integrity just due to sensor failure is not an easy problem. One of the thoughts that we've had on this is that it's probably best to work with raw data if you are the recipient of data being shared over a network. So raw sensing data has the benefit of being easier to model, to validate, and harder to fake because it has a whole lot of clues that might indicate fakery of the data. Of course, raw data also has the downside in that it's much more computation or bandwidth intensive when you send it across. Maybe 5G will open up the floodgates of communication between vehicles and between vehicles and infrastructure so that it becomes almost trivial to send a couple of gigabytes of data to another vehicle. But maybe it will remain somewhat costly going forward. And so there will be an incentive to move up from raw data to more processed data and maybe even interpreted data so that you can get it quickly and with low bandwidth to other vehicles. But as you move up to higher and higher interpretations, higher and higher levels of processing, it's much more difficult to prevent the data from being either maliciously or not corrupted. We believe that the ego vehicle can partially validate incoming data by just checking its consistency against that portion of the environment that the ego vehicle can see. And this can be done even if the incoming data was taken with a sensor that was not identical to the sensor in the ego vehicle. Sometimes even when it was taken from a sensor that isn't of the same sensing modality as is available on the ego vehicle. Now you might say, looking at this, you might say, well, you know, the vehicle, the data coming in is most valuable when it covers the area the ego vehicle can't see. So it's precisely in those parts where you have blind spots that you most need these data, and that's where you'll be at the greatest disadvantage in trying to validate the data, and that is all true. The hope is that there is enough overlap with the portions you can see, and some assumption of correlation across the data, so that if you validate what you can see, then you can make a good assumption about the integrity of the data that you can't see. But still, it remains an insoluble problem. Somehow there will have to be a network of trust built up. Somehow someone would have to suffer a reputational harm if they were to send over maliciously corrupted data. Here's an example of an effort to validate data even across sensing modalities. So on our Sensorium, we have radar data coming from three different types of radar, or two different types. And then we have data coming from our stereo vision system. You might ask, well, is there a possibility of validating these against each other? And we looked into this a little while back. You can see that the radar data are very sparse. And from vision, you can get also from some rather sparse feature matches between the stereo cameras. The radar data here are shown in blue, and the feature matches between the stereo cameras are shown in orange. There doesn't seem to be a whole lot of correspondence between the two, so that you would have the ability to validate the blue data with the orange data. But if you take the data over several sequences in, say, a 5-second interval, you find that there is quite a bit of correspondence. On the right, we have a little map built on radar returns. On the left, we have a map built out of the vision correspondences. And what we're really saying here is that those things that tend to show up in SIFT feature correspondences are often, not always, but often are showing up in the radar data because they're reflective. You can zoom in on some of these and see that there's quite a bit of correspondence. And this gives some hope that even if you have fairly dissimilar sensors, you might be able to double check some of the data coming in and give at least a thumbs up for reasonableness. But this isn't an exhaustive proof of that or anything. It's just kind of giving an idea that your sensors will be useful in checking the incoming data, even if they're somewhat dissimilar. Now on to the third of the problems in the trilemma. Cooperation is undesirable also because of the cost of data exchange. It's not just a cost of sending the data through the network, it's a cost of preparing the data and figuring out whether I've got data that you'd want and figuring out whether you've got data I might want. There's plenty of cost going on here, even apart from the security considerations. Here are some of the particular questions you might ask. How can cooperation be incentivized? How could we incentivize Waymo, for example, to open up their sensors and begin to cooperate when they appear to have no interest in that? And then who bears the cost? Does the buyer, does the seller, does some intermediary? Is this the responsibility of the government, given that it will have beneficial outcomes for the populace? And how should the data exchange be managed? We don't have all of the answers to these questions, but we think it's an interesting area of research, and we'll offer a few thoughts to kick off your thinking. We imagine there being a data exchange, much like a financial exchange where stocks are sold. This data exchange is where data are traded in exchange for some sort of compensation. Feeding the data exchange are all sorts of traffic participants and infrastructure. So you can have automated connected vehicles feeding data into the exchange. You can have infrastructure, radar and cameras built right into the semaphores or to the local light posts. And you can have transit vehicles that also contribute to this data being exchanged. Okay, so it's like the scenario that we showed earlier where the vehicle across the intersection has some data that I might want. Somehow I've got to tell that vehicle, hey, you might have data I might want, and that vehicle has to send the data over. You can already anticipate, I suppose, a host of complexity problems arising here. So let's take a look at this. Remember that from the perspective of the ego vehicle, represented here in red, what matters is the effect the data will have on the cost distribution. We'd like two things to happen. We'd like the cost distribution to have a lower mean, which means that the risk was reduced. But we also might want, we might value the cost distribution simply having a lower variance. So we care to have less uncertainty about how the cost is distributed. And exterior sensing can provide us with that, even if it doesn't budge the mean. So all of these things are valuable. And we could say, look, for the space of the area I'm inhabiting, my neighborhood, say the intersection that I'm facing, and for the time that, that starts right now, I would place a really high value on data at this location and at this time, and a lower value at this location and this time. And I might send out a request that says, hey, these are the basic areas that I'm interested in at these basic times. Okay, there might be vehicles and infrastructure in the environment that have data that, if they were processed in the way that I would need to process them, would provide me the, say, high value data up into this upper right-hand corner, or the lower right-hand corner, or the one here in the middle. But it's not so easy as to say, oh, I'll just grab the data and bring it in, because the value of the data is in the eye of the beholder. The value of the data is something that only the ego vehicle can assess. And if the data are sent to the ego vehicle, there's a cost that incurs to that. And maybe once they are sent, that's when the ego vehicle decides that the data weren't valuable after all. And so he or she is then faced with having to pay a cost for the data having been sent over, and it was something of an inefficient exchange. So there is a value cost trade-off for the exchange that has to be mediated by this exchange platform. And our question is, how best to bring this about? What is the smartest way that one could set up an exchange so that you can save lives, but at the same time make it efficient and low friction, so that you can incentivize participation? A couple of costs and complications to this. There is, as I mentioned before, there's a cost incurred by processing the data, aggregating it, and sending it over to the buyer. And then evaluating the data requires processing, but the value, as I said before, is relative to the ego vehicle. So the idea that we've had so far in trying to understand what a best approach to this problem is, would be that the ego vehicle doesn't necessarily want to perform the processing on the ego vehicle of data that are sent over when it's yet uncertain about the value of those data. Maybe better would be to send the processing to the data instead of bringing the data to the processing. In other words, we imagine the ego vehicle sends an agent to either the hosting, the host of the exchange, something that could be implemented near the edge of the network, or to the cooperating vehicle. This agent is an executable, a containerized application that can be run fairly effortlessly on the on either the exchange or on the cooperating vehicle's computational platform. And the agent can ingest local data and spit out a metric of utility of that data for the ego vehicle. It can also, it could do some pre-processing that might be the only thing that gets sent back to the ego vehicle, or it could do some pre-processing that gets sent back to the ego vehicle in addition to earmarking other raw data that it says ought to be sent back to the ego vehicle. It would be in the ego vehicle's interest to buy those data. And the idea here is that this pre-processing by the agent can enable the ego vehicle to get a quick look at the data and evaluate it before it commits to having them sent, having the data sent over and incurring the cost. But you might say, hey, wait a minute, this thing could be, this whole paradigm could be easily gamed, because somebody might send an agent over to a collaborating vehicle and say, hey, collaborating vehicle, run my agent, and once it's done, send me the little outcome, the little output. That'll cost you almost nothing because it's just lightweight, very little data. And then I'll tell you if I want to buy anything else. And the collaborating vehicle does so, sends the small product of the agent back to the ego vehicle, and then the ego vehicle says, never mind, right? Turns out the product of the processing was what was valuable to the ego vehicle, and it didn't require any further processing. And we don't want to limit the way that the agent gets used. So we wouldn't want to say, thou shalt send back only this kind of formatted data. and thou art required to send back or to buy this many megabytes of raw data. We don't want to limit the way that the agent gets used in those ways. So we simply want to develop a basis of rules whereby if the agent is run on the collaborating vehicle, the collaborating vehicle gets compensated for any computation time that is expended running that agent, and then gets compensated for any of the communications cost of sending the product of the agent or the identified raw data back to the agent. And from our perspective, it really doesn't matter, even if the ego vehicle is just sending the agent over to the cooperating vehicle to do some Bitcoin mining. It doesn't matter to us what kind of cooperation is, or what kind of computation is being done, so long as it's done in this containerized application so that it doesn't pose a threat to the cooperating vehicle. But it is important that the cooperating vehicle be compensated for any of the expense of running the agent, so that it doesn't become just some sort of a computer slave to the agent. Anyway, we believe that this is kind of the essence of breaking down the barriers to cooperation and to making it a low friction, high efficiency marketplace, that sending this agent across and then having the agent give a prediction for how the data will benefit the ego vehicle by changing the ego vehicle's cost distribution. That's going to be a valuable idea that we'll try to suss out in further papers going forward. So finally, a few takeaways from my presentation today. Cooperation, we believe, is essential to extremely low risk. It's not essential if you just want to keep the same sort of risk that humans have right now. We don't tend to cooperate except through kind of gestures and through indicator lights, but we don't have a way of getting a bird's eye view of an intersection, for example. And so if you want to get to, say, 100 times human reliability, we believe that cooperation is going to be essential to that extreme risk allocation. We also believe that a precise common frame pose is necessary, but it's possible. We can do that. That objection to cooperation can be overcome. Data integrity will be a key challenge, and we believe that raw data will be easier to validate and harder to fake than more highly processed data. And finally, we believe there will be data exchanges at the edge, and they'll play a role of trading platform where the data buyers and sellers can negotiate deals. And all of these particulars about the agent and how much compensation are yet to be worked out, and perhaps will be the fodder for many good papers going forward. Well, I thank you for listening, and I'm happy to take any questions.